Everybody. So today we're going to talk about the three types of chemical bonds. And of course, you've all heard of the three major types of chemical bonds before. So we have ionic bonds, you have covalent bonds, and we also have metallic bonds. But what makes all three of those bonds different from one another? Basically, what it comes down to is what types of elements form each of those bonds. So ionic bonds will occur between two different types of elements. Covalent bonds will form between one different type of element, as will metallic bonds. And we're going to discuss more of that in a second. And actually, you did do some of that back in your crash course on naming. So typically, ionic structures tend to form between metals and nonmetals, and covalent or molecular structures tend to form between all nonmetals. And that's really the best indicator that we have in order to determine whether a compound is going to be ionic or covalent is by looking at the elements that comprise it. However, another good way that you can determine what type of bond will exist between two elements is, of course, by looking at the electronegativity. So this is my favorite electronegativity chart that we have because it clearly shows the different values for electronegativity. And of course, where are your most electronegative elements? All the way over here by fluorine. So fluorine is super electronegative, especially because it's so small, it has a low atomic radius. There is a very large attraction from the nucleus to that second energy level, so that the increasing nuclear charge is what is drawing those electrons in so well for fluorine, which is why it's very electronegative. And the same thing for oxygen, chlorine, and sulfur. Of course, chlorine is not as electronegative as fluorine because those valence electrons on the outside are a little bit farther from the nucleus. And that's because those core electrons are shielding those outermost electrons. So the nucleus doesn't have as strong of an attraction for electrons in that outermost shell. This is another way of determining the type of bond that would exist between two elements. What I'm finding, though, is that although this is a good indicator, typically the best way to tell what type of bond occurs between two elements is basically what types of elements make it up. And as you see for ionic bonding, an ionic bond is a complete transfer of electrons from a metal to a nonmetal. And when that happens, you generate two oppositely charged ions. So notice that this is always between a metal and a nonmetal. And that, like I said, is the best indicator of determining what type of bond will exist. The reason why it's always a metal and a nonmetal is because if we look back at this electronegativity chart, your nonmetals have very high electronegativities, and your metals have very low electronegativities. So your nonmetals can basically rip an electron away from one of your metals, which is why you have that transfer of electrons that occurs. And when you have that transfer of electron that occurs, so you'll see here, this one would be the metal. This would most likely be an alkali metal because it has one valence electron in its outermost shell. This nonmetal would most likely be a halogen because this has 7 valence electrons in its outermost shell. And in order to stabilize both of those elements, of course, the nonmetal wants that last electron so bad, it's going to steal it from the metal. And when that happens, when this nonmetal is gaining a negatively charged thing, it itself is going to become negative, as opposed to the metal, which is losing a negative thing. It's becoming more positive. So here's how you could really show the formation of an ionic bond between sodium and chlorine. So typically you would want to draw their electron dot notation. So here's sodium with its one valence electron represented by that orange dot. And here's chlorine represented with 7 valence electrons. So notice you have a metal and a nonmetal. We'll draw the arrow there. And I'm just going to put these on the page so we could see kind of how this works. But chlorine, with its very high electronegativity, being a nonmetal that's really close to having a full outer shell, it's going to steal that electron away from sodium. So when that happens, sodium has a charge of +1, again, because it's losing a negative thing. A lot of people sometimes get that confused. They're like, wait a minute, well, why isn't sodium negative then? Because it lost something. again, it's losing a negative thing, so it becomes positive. If you get rid of all the negative things that happen in your life, you become happy. So, and the same thing goes for chlorine. So chlorine gains that negative thing, it's going to become negative itself. And the ionic bond is really the attraction between the positive and the negative charges, like a magnet. Positives and negatives attract. So when this transfer of electrons occurs, of course, you form sodium chloride. And we don't call that a molecule because typically you're not going to represent this by a line like you would in Lewis-Dot structures. And that's because they're not sharing their electrons. So I can't show this with a bond that's sharing the electrons between them because that's not what happens. So we don't call this a molecule, but we call this a formula unit. And again, these are not going to form molecules, like we said, because molecules want to share their electrons, and these are not sharing their electrons at all. But a formula unit is a lowest whole number ratio of ions that are represented. So basically, every one sodium atom will transfer its one electron to one chlorine atom. Thus, the ratio of sodiums to chlorine atoms in an ionic structure is 1 to 1. Thus, the formula unit is NaCl in a 1 to 1 ratio. And this is really what the structure of this would look like. So again, they're not going to form molecules like water or carbon dioxide. These instead are going to attract the other nearby ions. So if I take a look here at this chloride ion, surrounding this chloride ion, you would have all of these positively charged sodium ions. And the reason why it forms in this structure is because it wants to become more stable. They want to minimize their repulsive forces. If you have chloride ions surrounded by all other chloride ions, they're going to repel each other because positives and negatives attract. So your ionic structures are always arranged in a systematic, periodic 3D array that maximizes attractive forces and minimizes your repulsive forces. And the only reason why it looks like these chloride ions are touching is because this is drawn in 2D. It's kind of hard to see it when it's flat on paper. But in real life, this would look more like this. So this would be more of a three-dimensional structure. And the chloride ions are much bigger because they have that added electron. That nucleus can't pull that added electron in much closer. Thus, the radius is going to increase. Your sodium ions are much smaller for the opposite reason. So we could see here that this chloride ion, for example, is surrounded by all these sodium ions. It's arranged in a way that makes it the most stable. It's maximizing attractive forces. Each chloride ion wants to be surrounded by all positive ions in the same sense that the positive sodium ions want to be surrounded by all negatively charged ions, the anions. And that's because it's more stable that way. And this particular structure, you could see, makes a really organized cube shape. And if you were to look at sodium chloride underneath a microscope, or if you were to look at a very large piece of sodium chloride, which in the geology world, we call that halite. That's the mineral name for sodium chloride. There's like 800 names for the same thing in science. So sodium chloride equals salt equals halite. Here is a very big chunk of halite, and you can see that this forms a really nice cubic structure. And it forms that nice cubic structure because of the way the ions are arranged in this formula unit. So I always thought that was really interesting. And if you were to crack this piece of halite, it would cleave what it's called. That's called the cleavage of a mineral. It would cleave along these very flat surfaces because it takes on the structure of that crystal. This lattice structure is what it's called. So you can see everywhere, except for here, this looks kind of wonky right there, but everywhere otherwise forms a really nice cube shape, and that's because that's the crystal lattice structure of sodium chloride. Here's another example of the formation of an ionic bond. So this is between calcium and fluorine. So calcium is an alkaline earth metal, which of course has 2 valence electrons. And then we have fluorine, each which has 7 valence electrons. Now in this case, fluorine can accept the 2 electrons from calcium because one itself wants to accept only one. So what's going to happen in this case is, so I just re-put those there so you could see, one fluorine atom could accept one electron from calcium, and another fluoride ion could accept the second electron away from calcium. So in this case, it's not a one-to-one ratio. The formula unit is going to be a little bit different. When calcium loses two negative things, it becomes positive, and it'll be positive 2 because it lost two things. Each fluoride ion will have a charge of negative 1 because they each gained one electron. Therefore, the formula unit for this structure would be CaF2. One calcium ion or one calcium atom gives its two electrons to two different fluoride ions or fluorine atoms to make fluoride ions. So little bit different formula unit because the ratio of electrons is different in this case. And this is also an interesting one because this particular ionic structure looks like this. Now, if you look in the packet that describes what you need to know for this unit, you don't need to know the types of ionic structures like this, but I just wanted to show you the difference between sodium chloride versus calcium fluoride, or this is otherwise known as fluorite. So you notice that sodium chloride had more of that cubic structure. This one doesn't. This one has something totally different. And I don't remember the names of these because it is just a memorization topic. But in real life, what this would look like is something like this. It forms a structure that's totally different from sodium chloride. And that's because of the way the ions are arranged to maximize the attractive forces. So it's really, really interesting. And I was never that great at this type of chemistry, but I did always think it was really cool, especially because I love rocks and minerals. So maybe one day I'll sit down and I'll learn these a little bit better than I did. But this is why all of your crystals have very different structures from one another, and why they form different shapes is because of the way the ions are arranged in the crystal lattice. So it'll cleave along different surfaces, which is pretty darn cool. So here's calcium fluoride again, and just to compare, here's sodium chloride again. So totally different crystal lattice structures, which thus leads it to look a little bit different, which is pretty cool. Those are all for ionic bonds. The next is a covalent bond. Oops, I forgot to, whoops, didn't mean to make myself lecture. I forgot to put that animation, but it's okay. So covalent bonding. Ionic bonds occur between a metal and a nonmetal, thus have a transfer of electrons from highly electronegative from a very not electronegative atom, or one with a low ionization energy. Covalent bonds are different. So covalent bonds results from the sharing of electron pairs between two nonmetal atoms. So the best way to identify whether two atoms will form a covalent bond between them is by looking at the fact that they're made up of nonmetals. And there's really two different types of covalent bonding, because if you think about the electronegativity chart, you can have something like fluorine, which is super electronegative, bonds to a nonmetal that's not that electronegative, like hydrogen. So in that case, fluorine is a little bit stronger than hydrogen is, and therefore it can pull electrons more towards itself. So we can look at covalent bonds and bonds in general really on a spectrum. So if I have two of the same types of elements, or two elements that are really, really similar, they are going to form a nonpolar covalent bond. And a nonpolar covalent bond has an equal distribution of charge because the electronegativities between those nonmetals are really, really similar. As opposed to a polar covalent bond, this is when you have two nonmetals that have different electronegativities, but still not strong enough or not different enough to make an ionic bond. So in this case, we have an unequal distribution of charge. So here's an example of a nonpolar covalent bond. I have bromine bonded to another bromine atom. Neither one of those has a higher affinity for electrons because it's both bromine. So therefore, they're going to equally share their electrons between them. Neither bromine wants electrons more than the other, so there is an equal distribution of charge. Whereas if I had hydrogen bonded to bromine, bromine's electronegativity is much greater, and you can tell by looking at the electronegativity chart. And I don't have it in front of me, and I don't feel like going back. So I know it's probably in the twos or the threes at least. I think in the twos somewhere, maybe 2.7, 2.8. Hydrogen is 2.1. So their difference is, almost one, really, an electronegativity difference of almost one. So what happens is bromine's not strong enough to rip the electron away entirely, but it is strong enough to pull electrons towards itself. Think of it like a tug of war. So a lot of times when you're playing tug of war, one side is much stronger than the other, and it could pull the rope more so to win. And the same thing goes for elements in between these bonds. So bromine can pull electrons towards itself more so than hydrogen can. And what that does is we create partial charges. We make a polar molecule. So polar, again, means an uneven distribution of charge. One side of the molecule will have a partial negative charge. And that's what this little delta means right here. It's like an S with a little at the end, or like an unfinished 8. It's a Greek letter delta. This side of the molecule will have a partial negative charge because more electrons are going to live around bromine, as opposed to the hydrogen will have a partial positive charge. More of your electron density is going to be centered around bromine because it wants electrons more, but it's not strong enough to totally rip it away and create two ions like an ionic bond will. And notice here, the more electronegative atom, in this case bromine, pulls the electrons towards itself, thus making this side of the molecule the partial negative. That's a really important thing to know, are those partial negatives. More electronegative means it could pull electrons towards itself more, which means it would have the partial negative charge. These are how you can determine the difference or the type of bond based on the difference in electronegativity. But like I said, the best way to determine what type of bond would most likely exist between two elements would be if it's a metal and a nonmetal, it's ionic. And if it's two nonmetals, it's covalent. You can also be more specific by looking at the difference in electronegativity, but this isn't always that accurate. And that's because we have to think of ionic character versus covalent character in more of a spectrum. So up here, you form an ionic bond when you have very different electronegativities, and you're a nonpolar covalent bond when you have very similar electronegativities. So the difference between them is not always distinct, but we have to think of it, like I said, a continuum. So when you have your nonmetals that have the same or nearly the same electronegativities, they will form the covalent bond. Whereas if they're very different, it forms an ionic bond. And really, some compounds that are in the middle of their electronegativity, so if they're like right on the cusp of like 1.7, they could have characteristics of both. So it's kind of hard to differentiate them. But the best way to know if something dissociates or not in water or dissolves in water because of the charges is not always based on electronegativity, but it's always based on the type of elements that make it up. So ionic or metals and nonmetals is always ionic because their electronegativities are different. Nonmetals is always going to be covalent bonds. The greater the electronegativity difference, the more ionic character a bond will have. And generally, bonds between a metal and a nonmetal are ionic, whereas bonds between nonmetals are covalent, which we just talked about. The last type of bond is a metallic bond, and there's really one major thing you need to know about metallic bonds, and that's that their electrons exist in a sea of electrons. So you have these very closely packed, positively charged metal ions, and surrounding those metal ions is one giant cloud. And within that one giant electron cloud, all the electrons can move over or move around. We call that delocalized. So if you stayed local your whole life, you're probably going to stay in Hawley or at least in northeastern Pennsylvania. You're local, you're localized. If you're delocalized, You're moving around everywhere. You're visiting other parts of the United States. You're visiting other parts of the world. You like to travel. Maybe you move around different places. That's what delocalized means. You're constantly moving. And that's what is the key about the electrons in metallic bonds. So I don't like this image, so I actually have a nice video on the next slide that I'll show you, and it's really, really short. But you have your positively charged metal ions, and then you have these electrons that exist in this big cloud of electrons that surrounds it. Again, I don't think this picture really does it justice, so instead I'm going to show you this video on this slide here. So notice that these are potassium atoms. So they each have their one electron in that outermost shell. And what happens is those positively charged potassium ions, their electron clouds overlap, essentially to make one giant electron cloud. And therefore, each of those valence electrons, let's play that again, each of those valence electrons can move throughout that whole entire structure, which allows metallic solids to have the properties that they have. So metals are very malleable and ductile because the atoms can slide past each other very, very easily. They're also great conductors of heat and electricity because those electrons are always moving. So this is a really nice example, I think, because you can actually see the flow of electrons. And that's what delocalized means, is that it doesn't belong to one particular atom, but at any moment, the electrons are in any place. So each individual electron belongs to basically the whole structure. Like as that's moving, we can't really tell which electron came from which atom because they belong to the whole thing. In that same sense, we're going to talk about alloys here. And I want to talk about alloys because I noticed that a couple of the practice exams for the AP exam, they had you memorize the two different types of alloys that you can have. And they're very easy, but it's just a rote memorization type of question. So I figured I would throw it in here just so you've seen the two different types of alloys before. And what is an alloy? Well, alloys are new metals that are made by combining two or more types of metallic elements. But the reason why we make alloys is to give greater strength to those or to give resistance to corrosion. So, for example, steel, you will not find steel on the periodic table, but instead what it is it's iron that's combined with carbon atoms. And when we make that, when we combine the carbon atoms to the iron, it allows for it to become much stronger than it would be without them. And it might resist corrosion a little bit faster. Now, steel might still corrode, but it's not going to corrode as fast as elemental iron will. Other alloys you may have are brass, which I believe is an alloy of maybe zinc and copper. I know it's copper. Pretty sure it's zinc, but I'm not 100% sure. Sterling silver is another type of alloy. I've been starting to buy more vintage jewelry online, and I noticed that you know that something is sterling if it has the print of 0.925 on the inside. And the 925 stands for 92.5% silver. So it's not 100% silver because it helps to, silver itself is going to be very, very soft. So they typically use the 92.5%. So it becomes much stronger. Otherwise, it would probably bend very, very easily. And of course, I'm not wearing any of my silver jewelry today, so I can't even show you. But there's really two different types of alloys. This one over here, we can tell is not an alloy, that is a pure metal. And that's because all of those atoms are exactly the same. This one right here, so this is an alloy. And notice how, compared to the pure metal, we just have these different atoms that took the place of the other atoms to begin with. So some of these red atoms, whatever it may be, were replaced or substituted by these blue ones here. So we literally call that a substitutional alloy. And that's when atoms of a new element literally are substituted in for the original element. So, for example, you might have copper and nickel. And notice it does say that they have to have a similar atomic radius. If they don't have a similar atomic radius, you can see we get the next one. But that's because the new elements or the new metal can simply replace the old one because they're about the same size. As opposed to this second type of alloy, so notice how I have all of the same metal ions that I had in the pure metal. However, these little green atoms here, they're much smaller than the red ones and these blue ones if you're comparing. Because they're so much smaller, they can literally fit in the holes in between the areas of where those other atoms lie. Because they can fit in those holes, they're not replacing anything. There's just added there's added atoms to that. We call this an interstitial alloy. And that's when we have different or smaller metal atoms that they occupy the interstitial spaces, otherwise known as holes, in the lattice structure. And an example of that would be carbon and iron, which, like we said, is steel. So here's our substitutional alloy, where the one in the middle, where literally a new metal substitutes the original metal. Whereas the second one, interstitial, is when we have very or much smaller metals kind of take up the holes in another type of metal. So I did just want to tell you that because I did notice a couple of, like I said, rote memorization of these two different types of alloys. I saw a picture and it's like, which one of these best represents an interstitial alloy? And you had to identify from the picture which one that would be. So just keep a mental note of that. Those are the different types of bonds. If you have any questions, let me know. You will have an assessment on this in class, and of course, this will apply to a lot of the other things we are going to do in Unit 2. I hope this helps, and I will see you in the next video. Bye.